then we are going to the pressure. But what you should keep in mind is that this is for one particle and this is for all particles in the container. Then we should maintain this formula. For one particle. One particle. Then we can calculate for the pressure. And if we calculate for the pressure, it's gonna be easy because we know that the force acting on the surface of the wall, then the surface of the wall over pressure will be equal force over area. It's gonna be so easy if you know this. Then if we know all this formula, then we know that in the average velocity over the distance is equal to this. Then we know that pressure equal force over area. So what will happen if we divide all of this with area? And we will say that if the force of area, if we divide this, divide it with area, it's gonna be force over area, and we know that the length of this square will give us the area. And you know that we have number of particles, we have their mass and their velocity average squared x, and we have this other, and we are going to multiply because we divided, it is gonna multiply to this other square. This, because the area of this, it is the length, the area of the container, it's gonna be r times r. Then if this r squared times r, they can give us r cube, and give us another idea that the r cube means the volume, because if you have the volume, it's gonna be like the length of this container cubic. Then we're gonna have this force over area, it's gonna give us pressure, and we have number of particles times their mass times the average velocity over this, which gave us V, the volume. That's where we have PV, and look at this, it's gonna give us the formula of ideal gas. Number of particles, mass, V squared, and V comes from here, because the R gives us the R. Then that's how we can calculate the pressure of one particle of gas, and this will be the pressure of one particle gas. Then, no, I mean, this is for the total because it involves total number of, it is for total number of particles of the gas. If it is for one gas, there's no need of this A. Then, for this, we can calculate the velocity of the gas particles. If we want the velocity, it's quite easy from this formula. Then if we want to see the velocity, we should consider the dimensions of these moving particles, because these particles can move toward the x-axis, and then we have a vx, and they bounce back, and they can move toward the y-axis, and we have the particle moving with the speed toward y-axis, and they can move toward z-axis. They can move, in all dimensions. So actually we have 3 dimensions that this particle can move. So then we can calculate the total velocity of this gas. The velocity, which is total, the average, should be equal to the dimension of these particles. Particle moving toward the x-axis squared equal plus the particles moving toward the y-axis and the particles moving to z-axis, their average, So now what I want is how can I calculate this Vx? And because this, in ideal gas, the particle moving have equal energy. There is elastic collision. There is no loss or gain of kinetic energy. So the Vx squared is equal to Vy V squared Z. Then this will give us that the total energy V total is equal to 3 times Vx. Then if you want this, it's gonna be like Vx equal V total square, average of total energy, velocity over 3. And if you want to replace this into this formula, we're gonna have PV will be equal to number of particles times their mass times this V total over 3. Then that's where we can have this formula. 3PV equal to NMVX. And if we know this, and I'm gonna do some magic, what will happen if I divide this by 1/2? The magic will be that 3, if I over 2, because it is like 1/2 PV, it's gonna be N, and I do like this, M V total velocity square. And if you are looking very well, I did it intentionally to show you that this will be equal like kinetic energy of average gas particles. Average kinetic energy. Then you can subtract. It will be 3/2 PV. It's gonna be number of particles times kinetic energy. Average kinetic energy of the particles. Then if you have this, we know that this PV from ideal gas PV equal nRT. You can, this N, it is like this, number of particles. Then you can subtract this into this. And the PV also is equal, PV, it equal number times Boltzmann's constant times temperature. Then we're gonna have 3/2 will be equal to N number of particles, Kb, Boltzmann constant, number of mole times kinetic energy of particles. Then if you cancel this, we're gonna have this 3/2 Kb. It's gonna be like kinetic energy, average kinetic energy of particles. Because once you have all of this, you can calculate the kinetic energy of the particles in the site. Then you can also do this. It will give us the same answer. Then we're gonna be PV over nRT equal N times Ke average. Then you cancel. The question gives us RT equal Ke times E average. That's how you can calculate the average kinetic energy of gas particles in the container.